So there's two more definitions that I want to introduce before we conclude this section, and the next one is something called the transpose. So let's start with a matrix, and we'll write down letters that represent its dimensions. So let A be an m by n matrix, and we're going to say what its transpose is. So the transpose, that's the term for this, and the notation for it is we just write the letter A, so whatever matrix you're starting with, write it down, but then write as a superscript a capital T, and that just stands for the transpose. So this is the notation for the transpose, but you're taking a transpose of some matrix that you started with, so that's what I'm going to say, of A. So this is the notation for the transpose, this is the matrix that you started with in the first place. So what is the transpose? Well, it's another matrix, and its dimensions are going to be n by m. So that's the first thing you'll notice, right? The dimensions of A transpose that I'm putting right here, they're the same as the dimensions of A, except they've been flipped, right? So the number of rows of A transpose is the number of columns of A, and the number of columns of A transpose is the number of rows of A. So that's just the dimensions, that's not the definition, so we still need to state what the rule is. So here it is. So if I want to get an entry from A transpose, let's say I want to get the entry that occupies the jth row and the ith column. Well, the definition of that is going to be just take the entry from the matrix A that happens to be in the ith row and the jth column. Okay, so the indices are flipped. So, let's finish the sentence and then we'll come back to exactly how these indices are used. What is this rule valid for? Well, it's got to give us a valid rule to determine the entry of A transpose with who's in row J. So J would have to be between 1 and the number of rows of A transpose, so between 1 and n. And then the column index would have to be between 1 and the number of columns of A transpose, which is m. So this is true for each I and j, such that I is between 1 and m, and j is between 1 and n. And of course, you can, just as a check, these will be exactly the bounds that ensure that the I and j make sense over here on the right-hand side of this equation. So because I has to be an index for a row of A, and A has m rows, so I has to be between 1 and m. And j is a column index in this context, so it has to be pointed to an appropriate column, and A has n columns, so it better be between 1 and n. So this really is using the indices in the way we meant to. I didn't mean to do that little dot under the j, just ignore that. Okay, an alternative phrasing though for this, there's a simpler way to say this whole definition, and I'm going to deliberately say it now before we do our examples. You could say this a whole lot simpler. Just say the following. The rows of A transpose are the columns of A. That's another way to just phrase transpose. Okay, I could have also said the columns of A transpose are the rows of A. That would be another phrasing that's equivalent and would also work, but I'm not going to write that one down. I'll just write this one down. So, examples. Let's clarify with some examples here. So, I'll write down a few matrices. So I'm going to write down the matrix A. It's going to be a 3 by 3, 1, 0, negative 2, 4, 0, and negative 3, and then the last row will be negative 1, positive 1, and 4. So that's the first matrix A. Then I'm going to write down a 3 by 2 matrix B, and the rows are as you see here, 2, 3, 1, 4, and 5, 6. Two more matrices. The matrix C is going to be a row matrix, 1, 3, 5. And then I'm going to make one last matrix, D over here, which is actually a 1 by 1 matrix. It's got one row and one column. It's really just a single number. Let's take the transpose of each of these. So the transpose of A, well, You can follow this rule. You can follow this rule carefully if you like, or you can just follow the blue comment, which just summarizes it. The rows of A transpose are going to be the columns of A. So here are the columns of A. So turn those into rows, and that'll be your matrix A transpose. So for the first row of A transpose, I'm going to use the first column of A, which is 1, 4, -1. Right? That's the first column of A. The second column of A, I'm now going to write as the second row of A transpose. Then the third column of A will now be the third row of A transpose. So that's A transpose. For B transpose, well, B is a 3 by 2 matrix, so this definition tells us to flip the dimensions to get the transpose's dimensions. So B transpose is going to be a 2 by 3 matrix, since B is a 3 by 2 matrix. Okay, so just do the same idea. So we're going to have a 2 by 3 matrix. So I could just take the rows of B and turn them into columns. 2, 3, 1, 4, and 5, 6. So that's B transpose. C transpose will just be the column. Now, same entries, but now they're just in a column instead of a row. So, and in general, if I take a row matrix and take its transpose, I'm going to get a column matrix. And if I transpose a column matrix, I would get a row matrix back. Lastly, what about D transpose? Well, D is a 1 by 1 matrix. So if you start with a 1 by 1 matrix and you flip the dimensions, you're still going to just have a 1 by 1 matrix. So, okay, great. Now if I just say, okay, the rows of D transpose are going to be the columns of D, I'm really just going to end up copying that exact same entry. So in this case, D transpose is just ended up being the same as D, and that'll happen sometimes. So that's just roughly what that's not roughly, that's exactly what transpose is, but that's a brief summary of it. You can practice working with it on the exercise sets. I'm going to add one more definition, and then that will conclude this section. And this definition requires us to start with a square matrix. So what is a square matrix exactly? Well, it's a matrix that has the same number of rows as it does have columns. So let A be n by n. Quite often I'll start by saying let A be m by n if I want to state a general setting for a matrix. But in this case, I didn't use the letter m, I used n for both the rows and columns. So that's how you know, it's going to be something like this, right? This is an example of a square matrix here and here. They're both three rows and 3 columns. So if the number of rows and columns is the same, it's a square matrix. So these two are not square. None of these 4 are square matrices. These two are examples of square matrices, and so are these. Right? This is a 1 by 1 matrix and a 1 by 1 matrix. Those are square. So let me add that in as a comment. In other words, this just means A is square. So now you know what a square matrix is. Okay? Well, if you have a matrix and you know it's square, you could write out its entries, something along the following lines. Right? I don't know what the entries are in general, but I could just use notation for them. So how about the first row? I'll say A11, A12, and I'll go dot, dot, dot all the way to the very last entry in the first row, which I'll write it as A1n. Now the second row would be similar. I'd have A21, second row, first column, A22, all the way to the very last one, A2n. Yes, that's the second row. And I'll just keep on going until I get to the very last row, which first one will be AN1, using n because I'm in the nth row and the first column. Last row, first column. Then I'm going to have last row, second column, all the way to the very last entry in the bottom right corner will be the last row and the last column. So n will be the index for both the row and the column for that last entry. Now, what I want to highlight to you here are these entries. The entries that start on the top left corner and work their way down to the bottom right. This is called the main diagonal. Let's write that down as well. That's an important piece of terminology of the matrix A. So I'm talking about that right there. So that's what the main diagonal is. And that's what we're going to use to define this new term, which is called trace. And here's the definition. So the trace of A. Now this is only defined for square matrices. And you know that because the definition started with the assumption that you had a square matrix. So none of this applies to anything that's not already known to be a square matrix. So what is the definition of the trace? Better finish that. So it is defined by, so the notation I'll use, I can fit it in here. I just do TR, short for trace, and then I put the matrix in brackets afterwards. And this is just the notation for saying I want to take the trace of the matrix A. And all it is you just add these entries up. Add the entries on the main diagonal all up. So we have notation for that. It's all the entries whose row index and column index are the same. So 1, 1, 2, 2, next one would be A3, 3, and so on, all the way to the very last one, ANN. So you're really just taking the sum from j equals 1 to n of AJJ, right? And if you expand that sum, you just get A11 plus A22 all the way up to your very last one, ANN. So I barely fit that on that one line. But this is the definition, and this is just, by the way, if you expand the sum, this is what you get. Okay, so let's look at a couple of examples. So our first one, we'll take the trace of a 3 by 3 matrix, and here are the entries. So what's the trace? Well, we just said it's the sum of the entries along the main diagonal, right? So it's just going to be 1 plus 4 plus 0, which just adds up to 5. Right? So that's all there is to it. The trace is a nice operation because it's fairly quick to compute. What about another example? So this is an example of a 4 by 4 matrix. So the first row is 4, 2, negative 2, 1, and 0, 9, negative 1, negative 1, 3, 4, 0, negative 1, and then 1, 1, 9, and 1. So that's our fourth row. So that is a 4 by 4 matrix. What's the trace? Well, the trace, same thing, right? Just add up all the entries in the main diagonal. The 4, the 9, the 0, and the 1. So that is going to add up to what? 9 plus 1 is 10, so you get 14. So that's all there is to trace, really. It only works for square matrices. You'll never take a trace of a matrix that's not square. That's important. But what is the point of trace? It's just a nice numerical measure you can immediately associate with any square matrix that's easy to compute. That's the key factor here, right? It doesn't take a whole lot of complexity to just take all the entries along the main diagonal and add them up. You get to ignore most of the matrix, right? All the stuff down here and all the stuff up here gets completely ignored. So down here, for example, all these entries, they didn't play any role in the trace, and neither did the ones above the main diagonal up here. So that's what the trace is. And that's the end of section 1.3.